Okay, in this video, I would like to show you how to create a very simple model of a continuously stirred tank reactor with a reaction, basically with a pollutant that undergoes a decay reaction. In this example, I'm gonna consider second order decay, but you can apply the same techniques to create your own model with any kind of simpler or more complex reactions. So I'm actually working on a Linux machine, but you can do the same exact things on a Windows machine. So first thing, I'm going to open GIFMod. What I'm going to do is that for my continuously stirred tank reactor, I'm going to use a pond block. Even though you can use any other or many of the other types of blocks that is provided in GIFMod as well. But I'm just going to use a pond block, and in this case, that shouldn't really matter, as we are using a prescribed flow. Basically, our hydraulics is going to be completely controlled. So I'm going to add a pond. So this is a pond. I mean, you can basically keep the default name that is given, that is called pond 1, or you can change the name of the pond to anything you want. So I'm just going to call it my pond. And then I'm going to provide some information about the pond. So let's say this is a pond with a bottom area of 10 and an initial water depth of equal to 1. Now you can't see the full names of these properties completely in the table, but if you move your mouse cursor, you should be able to, this tooltip should show you the full name. So this is the initial water depth. So that's all I need for the pond. Now the next thing is I'm gonna introduce the chemical constituent that we want to simulate. So what I'm gonna do is that I will click on the water quality, and then I click on basically right click on constituents, and then I click on add constituent, and I'm gonna call my constituent, so change the name from constituent to, let's say, can be anything your pollutant is. I'm going to use PCB. So let's say the constituent that I'm working on is PCB, even though the parameters that I'm going to enter have nothing to do with PCB, but just as a generic name for a generic pollutant. So this is what we have. We have PCB in the system. I can now go and let's say add an initial condition to the pond, initial concentration. So in order to do that, I'm gonna select the pond, and then if you look at the properties, you can see this item called constituent initial concentration. If I click on this, bottom with 3 dots on it, I can say, that's the only constituent I have. So PCB has a concentration of, let's say, 10 milligrams per liter. Okay, so that's going to be my initial concentration in the pond. The first thing I'm going to do is that I want to run this model as a batch system, and then I'll go ahead and add an inflow and then an outflow. So next thing I want to basically indicate my reaction. Now, in order to do that, I'm going to click on reactions. I have 2 items here. One is reaction parameters, and the other one is reaction network. So the first thing, it's always useful to provide the reaction parameters as parameters. I mean, you can always also enter real numbers into the reaction network, but this is a much better practice. So what I'm going to do is that I want to enter the parameters for the reaction rate constant. So what I'm going to do is that I'm going to right click on reaction parameters right here, and then I'll click on add reaction parameter. So now I have a reaction parameter right there. I can call it anything I want. Now I'm going to call this is my decay rate. So I'm going to call this K sub D, right? So there's another property called temperature correction factor, or Arrhenius constant. This is when we know that the value of Kd is governed by temperature, or is affected by temperature. If the value is other than 1, then then we know that. In this case, I don't want to provide any temperature time series, so I'm going to just keep the temperature correction factor to be 1. And the value of decay rate, let's say the value of the decay rate is I don't know, let's say 0.75. Okay. So this is 0.75 per day. It also depends on the basically the unit of this. It depends on the reaction expression that I enter. So if it's a first order reaction, then the unit of this is going to be per day. If the reaction rate is a second order reaction, for example, which is what I'm going to provide here, it's basically the unit of this value is going to be 1 over time over concentration unit, which let's say it's milligrams per liter. So then the next thing is I want to indicate my reaction. So I'm going to just right click on the reaction network, and I'm going to click on open reaction network window. So this table shows up, and then I'm going to have only one process, and that is the decay of PCB. So as the process, I'm going to type, let's say, decay. For the process rate, if I want to do a second order reaction, the way it will look like is, of course, KD, which is my constant, times, let's say, the concentration of PCB to the power 2. And then the value under PCB is going to be the stoichiometric constant for PCB. I'm going to enter a value of -1. Now, the negative value means that PCB is being consumed and not produced. If I have a daughter products, then I can have another process, and then the stoichiometric value is going to be a positive value. So this is basically, we are essentially done with the reaction. Now, what I can do is that I can just run the model right now as a batch system. So I'm going to just save this as, I'm going to save it as decay example.gifmod. Okay. So now I can run. Actually, the other thing that I'm going to do is that I will just increase the simulation period. It's by default it's just 1 day. So if I run this, the model is going to be run for one day. But I'm going to run it for 10 days. So basically, I'm going to just now, in order to enter a number here instead of a date, if I click here, it's going to ask me to provide a date, but that's not what I want to do. I just want to run the model for a generic 10 days period. So in order to do that, I'm going to right click on simulation end date, and I'm going to click on input number, and I'm going to input a value of 10. So that makes the simulation period 10 days. Okay, I don't need that. Save it again. Now let's run it. So just click on this run. So I just ran the model. Now the hydraulic results, it's not very interesting. I mean, if I can look at, let's say, the storage in the pond, and what I'm going to see is that 10 cubic meters throughout the simulation period. And the reason is that we don't have any inflow and outflows. I can look at concentrations. So let's say I look at the concentration of PCB here, and that's what you see. So we start from 10 milligrams per liter, and then we have a decay, we have a dynamics in the change of concentration that corresponds to a second order decay reaction. I can also look at the mass of PCB inside my pond. So it starts from 100 and then it goes down. Okay, so this is when I want to do basically I want to simulate my model as a batch system. Next thing, what I want to do is that I want to provide some inflow and outflow, right? So now, in order to provide an inflow and outflow, we need to create some text files, right? So I'm going to use this text editor in. So let's just open my text editor. So this is my text editor. Now, my inflow is going to have two time series. One is the flow rate going into the pond, and the other one is the concentration of PCB. So now in order to say that, basically I'm going to add this line at the beginning of my file called names, and then the first time series is going to be flow, and the second one is going to be PCB. And then the table is going to have the file is going to have two columns. I'm sorry, actually 4 columns in total. Basically each pair of columns represent a time and then the corresponding value, right? So the first column is the time corresponding to flow, which I'm going to start from 0, and then let's say the flow rate is 0.2 cubic meters per day. And then the third column is a time for PCB, which I'm going to also say 0. And then the value, let's say, is 3 milligrams per liter. So we have 3 milligrams per liter PCB concentration inside our inflow. And I'm going to make this inflow file or inflow time series pretty simple. I'm going to only provide 2 data points, and then everything else, everything in between is going to be interpolated. So, and I'm looking for a constant flow rate going into the pond and a constant concentration of PCB. So my second row is going to be quite similar to the first row, with the exception that the times are going to be 10, which is the end of my simulation period, right? So so that's it, and I'm going to save it as, let's say, inflow. I'm going to save it in my documents, and I'm going to save it as inflow pcb.txt. Okay, I already had that file, so I'm replacing it. So that's what I have for the inflow. Now I can add this inflow to my pond and then run the model and see what happens. So I'm just gonna leave this open, and then what I'm gonna do is that I will click on my pond, and then I scroll down on the properties window, and then there's this item called inflow time series. If I click on this box in front of it, I can just go and select the file that I just created, which was called inflow PCB right there. To make sure that everything is working fine, I can just right click on the property value, and I can look at my flow, which is I think it was 0.2, I don't know, something like that, yeah. 0.2 over the simulation period. And also I can look at the PCB concentration, which was 3 over the simulation period. Now I can actually run the model. So I'm going to save it and run it. So this is what we get. This is actually a time step that is increasing because it's a pretty simple problem. So now what I can do is that I can look at some hydraulic results. I mean, now I expect my storage to change because I have a constant inflow going to the pond. So as you can see, the inflow is the storage is linearly increasing as we expect. I can also look at the concentration of PCB, which this is what I get. Now the thing is that I don't expect the steady state concentration to be now 0. It's going to be different than 0 because of the fact that they have some constant inflow of PCB going to the system. Okay, so next thing, I want to also add an outflow, right? So in order to add an outflow, what I need to do is I need to have another storage, another block that I divert the water from the pond to. So I can't have an outflow, I can't have a connector to nowhere, right? So basically what I'm going to do is that I will just add this second pond, and let's call this pond, I don't know, let's say effluent, because it's going to store our effluent. I can still, provide some information that are needed. So I'm going to say bottom area is 10, initial water, I mean, it doesn't really matter. I'm going to say maybe 0.1 meters initial water in the effluent pond. So that's what we have, and then the next thing is I want to now connect my my main pond to this effluent pond. So I'm gonna have this connector. Now for the connector, what I'm gonna do is that I will just I want a fixed flow, right? I want the flow to be fixed, equal to 0.2, just going out. And in order to do that, basically what I'm gonna do is that I will change the type of this connector. I'm gonna change it to prescribed flow. That means the flow is prescribed. And then I need a file to provide the information on the prescribed flow, which can be transient. It can change with time, but I'm gonna just use a fixed one. So now what I'm gonna do is that I will create this text file that contains my prescribed flow. So actually it's gonna be pretty simple. I'm gonna use this the file that I just created. In this case, I don't need the concentration for the prescribed flow. All I need is one time series for flow. So what I'm going to do is that I'll create a new file, and all I'm going to do is that I'll get rid of the PCB column, and I'll get rid of the two last columns of my text file, and that's what I have. So now I'm going to save this as, let's say, I'm going to call it prescribed flow.txt. Replace, and now I got the prescribed flow time series data. So I'm going to go back to GIFMod, and then I'm going to select this file for I'm sorry, actually it was called prescribed flow. I'm going to select the prescribed flow.txt as the flow going through this connector. Say okay. Okay, so everything is now ready. I can run the model. Okay, so here it is. Okay, so the simulation is finished. Now I expect the storage to be constant. So because the inflow and outflow are equal, so if I look at the storage, I'll see that it's equal to 10 throughout the simulation period, and that's what I expect. And I can look at the concentration of PCB, which if you see, okay, that's this is what we see now. What I can do here is that I can, let's say we have a condition where there's no initial PCB in the pond, so I can actually go ahead and make the initial concentration of PCB in the pond equal to 0, and I still expect the concentration to reach a steady state because I have some PCB concentration in my inflow. So I'm going to save this, run the model again, and you can now go and look at the concentration of PCB, and as you can see, it starts from 0 and it keeps increasing. Now in order to reach a steady state condition, I better decrease the hydraulic retention time in my pond, which means to increase the volume of water in the pond. So if I decrease the bottom area to 1, now I have a CSTR with 1 cubic meters of storage, and I can just run the model again, and now if I look at the concentration of PCB, I reach to a steady state concentration of around, let's say, 0.80 something. And that was it. If you have any questions, feel free to go to www.gifmod.com, questions, and post the questions, or just contact me directly. Thank you for watching.